So this is the final part of the assessment standard for Trig. This video is in 3 parts. I will be introducing you to 2 trigonometric identities. I will be explaining to you how you can use those trig identities to simplify expressions involving trig, and I will also show you a way to calculate exact values for special angles, which I have briefly mentioned, and these exact values are how you would solve trig equation questions in a non-calculator paper. Okay, so what we have here is a right angled triangle, and the sides are labelled hypotenuse, opposite, and adjacent. And we have the angle x highlighted. Okay, there are 2 trig identities that we can gather from this image. Okay, the first one is sine squared x plus cos squared x equals 1. Okay, and I'll prove this one to you. Sine squared x is equal to your opposite over your hypotenuse. And if we square that, and then we do the same with cos squared, we get our adjacent over our hypotenuse. Square that. Now we know when we multiply a fraction by itself, all we do is multiply the top line, multiply the bottom line. So what we end up with is O squared over H squared plus A squared over H squared. Don't know why I did that. Okay, so writing that as a single fraction, we get O squared plus A squared over H squared. Rules of Pythagoras say that H squared is made from doing O squared plus A squared, so we have H squared over H squared, and anything divided by itself is 1. Okay, so we have proven that trig identity there. That cos squared x plus sine squared x equals 1, or that sine squared x plus cos squared x equals 1. Either and or are perfectly acceptable. Okay, the next one we have is that tan x is equal to sine x over cos x. Okay, right, so trig tells us that sine x is opposite over adjacent, sine x is opposite over hypotenuse, and cos x is adjacent over hypotenuse. If we divide by h on both sides, or both sides of a fraction, it's like we never divided by h at all. And we've ended up with O over A, which is tan x. So that's our second trig identity. That sine x over cos x equals tan x. Okay, and we can gather 2 further trig identities from the first one that we have here. Okay, if sine squared x plus cos squared x equals 1, then if I get my pen tool back, then sine squared x is equal to 1 minus cos squared x, and likewise cos squared x is made from 1 minus sine squared x. Okay, any questions that you do involving trig identity are exam standard A-B questions. Okay, the majority of people will not answer these questions. Okay, but if you're looking to do higher, then it's strongly encouraged that you understand and are able to use these 2 trig identities. Okay, so I'm going to show you exactly how they are used. I'm going to change the color of my pen. Okay, so we have 3 cos squared x plus 4 equals 7 minus 3 sine squared x. Okay, what I'm going to do is I'm going to say that I have my left-hand side. And my left-hand side is equal to 3 cos squared x plus 4. Okay, and what I want to do is create a situation where that cos squared x somehow appears as a sine squared x. And how I'm going to do that is by looking back, I know that cos squared x is equal to 1 minus sine squared x. So I'm going to swap out that cos squared x for a 1 minus sine squared x. Okay, right, so I need to do 3 times that because there was 3 sets of cos squared x, so I need 3 sets of 1 minus sine squared x. If I multiply that out, I get 3 minus 3 sine squared x plus 4. Now we're starting to get something that looks very similar to this. And then 3 plus 4 is 7, so 7 minus 3 sine squared x, which is our right hand side. So what we have now is thus proven. And that's what those 3 dots mean, thus proven. Okay, right, moving on to the next example. Although this one looks more difficult, we're still going to go through those exact same steps. Okay, so we're going to have our left hand side, and that's equal to cos cubed x plus sine squared x cos x. Okay, right, so anytime you see any kind of expression involving x, the one thing you should be looking for is can we factorize it? And in this case, we can because we have cos x as a common factor. If I take cos x out as a common factor, I get cos squared x plus sine squared x. Looking back at my trig identities, if I go back the 2 pages, sine squared x plus cos squared x equals 1. And this just becomes 1 times cos x, which is cos x, which is our right hand side. And again, that's proven. Okay, so these 2 examples have all been involving the sine squared x plus cos squared x equals 1 identity. What about applying the tan equals sine x over cos x identity? So starting the same way, we've got left hand side equals 1 over tan a. Well, tan a can only be replaced with 1 over sine a over cos a. And 1 over a fraction just turns that fraction upside down. So we get cos a over sine a, which is our right hand side. And again, that's proven. Okay, and then one final example. We have 1 minus tan a is equal to cos a minus sine a over cos a. So starting the same way we have for all the others, we've got left hand side is equal to 1 minus tan a. Okay, so the only thing we can substitute tan a for is 1 minus sine a over cos a. What we're looking for is one single fraction, so I need to find a way to turn this into a single fraction. And I do that by changing the 1 into cos a over cos a. I've created that situation where I have a common denominator, cos a, and then I've maintained the value by making sure that it's something over itself. And if I tidy that up, I have cos a minus sine a all over cos a, which is our right hand side. And again, we're going to whip out that awesome little statement, thus proven. Okay, so that's how we apply trig identities. Okay, they're really, really straightforward if you really understand what it means to do a substitution. Okay, right, let's move on. The last thing that I said I wanted to look at, if we move back, is to have a way of calculating exact values for special angles. And that's what we're going to look at now. Okay, right, so I have two triangles here. I have a right angle triangle, which is isosceles, both sides. Both angles are 45, so I have an isosceles right angle triangle. And then on the other side, I have a equilateral triangle, which I have cut in half to create a right angle triangle. Okay, this triangle is isosceles, so it means that this side and this side are the same length. So both sides are length 1. By applying Pythagoras, we get 1 squared plus 1 squared, which is 2, and we want the square root of that, so this side is root 2. From this, I can generate sine of 45, cos of 45, and tan of 45. Okay, so sine of 45 is my opposite divided by my hypotenuse, so it is 1 over root 2. Cos of 45 is my adjacent divided by my hypotenuse, so it is also 1 over root 2. And tan of 45 is my opposite divided by my adjacent, 1 over 1, which is 1. Okay, moving on to our equilateral triangle. If that is 60, then in here is 30. It was an equilateral triangle, so all sides were length 2. If I cut one of the sides in half, it means that this side is length 1. Applying Pythagoras, it's going to say that 2 squared minus 1 squared, which is 3, and then square root it, and we get root 3 is the length of this side here. Now I can use this one triangle to generate sine of 60, cos of 60, and tan of 60. But I can also use it to get sine of 30, cos of 30, and tan of 30. Okay, right, so let's have a look. Sine of 60 is our opposite divided by our adjacent, so it's root 3 over 2. Cos of 60 is our adjacent divided by our hypotenuse, so it's a half. And tan of 60 is our opposite divided by adjacent, so it is root 3 over 1, which is root 3. Okay, sine of 30 is our opposite, which is 1, divided by our hypotenuse, which is 2. Cos of 30 is our adjacent, which is root 3, divided by our hypotenuse, which is 2, so root 3 over 2. And then tan of 30 is opposite over adjacent, so 1 over root 3. And do not take that to be negative, that was me making a mistake. That's not a negative, it is 1 over root 3, not negative 1 over root 3. Okay, so those are your exact values. I would not recommend memorizing the exact values. I would recommend memorizing those exact value triangles. Okay, so if we go back to the start, we can evaluate where we are at. So I have introduced you to the two trig identities. I have shown you how you use them to simplify expressions involving trig, and I've shown you a way of calculating the exact values for special angles, and we call that the exact value triangle.